asynchronously. And with that, I can ask our Zoom masters to proceed to the last talk of this session. It's about disaggregating solar generation using smart meter data and proxy measurements from neighboring sites. The talk is going to be given by Xinlei Chen. He is a master student at the University of Alberta in Omid's group. His research focus is on energy disaggregation, and he's also interested in applying machine learning techniques for tackling climate change. So if I can ask Faisal to please show us this talk, that would be great. Thank you.
Hello, everyone. I'm Xinlei Chen from University of Alberta. Today, I'm going to present our work called Disaggregating Solar Generation using smart meter data and proxy measurements from neighboring sites. This is a joint work with Moosa, Moghimi, Haji, and my supervisor, Omid Ardakanian. In recent years, as the cost of solar panel decreases, more and more residential customers choose to install their own rooftop PV system in order to save the bill. However, high penetration of PV introduces new challenges for planning and operation of power distribution networks. Therefore, it requires the system operators and the utilities to find a way to monitor and forecast the solar generation. But in the real world, most of the residential PV systems are behind the meter. Meanwhile, many customers do not report their solar panel installations or are unwilling to share their generation data with utilities. So the only data can be collected is the net load data, which is difference value between aggregated appliance load and solar generation. Here, the solid arrows shows the direction of power flow. In order to increase the observability of the residential solar generation, the first choice for utilities obviously is to install separate meter to measure the solar generation in each customer's home. But this method not only raises the privacy issue, but also is costly. A low-cost and non-intrusive method has been proposed called solar generation disaggregation method. This type of method aims to directly decompose the customer's net load into home load and solar generation. In our case, it is about customer-level solar disaggregation. The right-hand side figure shows the result of solar disaggregation. One biggest challenge for this problem is that it requires to be solved in an unsupervised or semi-supervised fashion, since we do not have any historical data regarding solar generation and home load from target home. Current solar disaggregation methods can be categorized into physics-based modeling approaches, which use physical PV model to estimate solar generation, and the another ones are black box modeling approaches. As far as we know, some of our previous work have been trying to use solar proxy measurements to estimate solar generation. We call them proxy-based method. Here, solar proxy means the monitored PV system installed in the same city or same district as the target home. However, there are some issues in those proxy-based methods. First, some of these methods are designed to address distribution-level solar disaggregation. Even though those two levels disaggregation solve the same problem, solar generation from single home is more volatile compared to distribution level aggregated solar generation. Second, some require the knowledge of deployment characteristic of target home's PV system, like tilt, orientation, and panel size. As we know, this information is not always available in practice. Lastly, most of them use proxy measurements from real sites only and do not fully investigate disaggregation performance for different solar proxy settings. Before we dive into the detail of our method, there are the two most significant contributions of our work. First, we introduce a data-efficient method for proxy-based solar disaggregation that relies on direct solar measurements from as few as one neighboring PV site. Second, we show how the solar disaggregation accuracy can affect the performance of NILM techniques. In order to make our method more applicable to the real-world situation, we make 3 assumptions. First, we do not know anything about customers except their approximate location and their net load data. Second, we also do not know the deployment characteristic of behind-the-meter PV systems. Third, there is at least one separately metered PV system in the same city or district as our target home. We believe this is not a strong assumption, since utilities usually have access to direct solar measurement from several sites in a city. Here are the 2 models we use for solar and home load estimation. First, we estimate the solar generation at target home using a mixture of measurements from solar proxies. The tuition behind is that PV systems in the same geographical area have more or less the same generation pattern, regardless of their deployment characteristic. Here, W is the weight vector of the mixture model. X superscript S is the matrix contains all the generation measurements from solar proxies. For home load modeling, we choose to use random forest regression model based on our preliminary experiment results. Here, X superscript L is the load-related feature, which includes temperature and time information. In order to better understand how deployment characteristics of PV system affect the PV output, let's take a look at these 3 figs. As we know, there are 3 main characteristics, which are orientation, tilt, and DC rating. DC rating is the maximum solar generation the panel can produce under standard test condition. It depends on the physical property of the panel, like the size of panel and the material of the panel. As we can see, tilt and DC rating only affect the scaling of the generation, but different orientation value will shift the peak generation time earlier or later. Therefore, solar proxy-based method like ours requires us to select more solar proxies varied in orientation. However, proxy measurement from a large number of neighboring PV systems might not be available in practice. To address this issue, we combine the measurement from real solar proxy with the measurement synthesized by physical PV model. More detail will be provided later. This is the whole framework of our method. Basically, it can be divided into 2 steps. The first step is to initialize the weight vector W of our solar mixture model using net load data from target home and solar generation of proxies. In this step, we utilize the solar TK to estimate the characteristic of PV system in target home and proxies. Then we use those estimated information to initialize the weight vector by the observation we made on previous slide. Solar TK is a open source data-driven toolkit for solar performance modeling and forecasting. Since we do not have the exact location information and only have the net load data from target home, the estimated results may not close to real value at all. But a good initialization still can enhance the performance of disaggregation method and reduce its convergence time. The second step is to iteratively estimate the home load and solar generation until the parameter of our models converge. As we can see, in each iteration, we recalculate the estimation of solar and load components by the equality constraint that net load is equal to the load minus solar generation. Then we can update the model parameters on these new estimations. In order to evaluate the performance of our method, we use All-Grid dataset. This dataset contains half-hourly home load and solar generation data, and has 140 customers with rooftop PV system in Sydney, Australia. We evaluate our disaggregation method in both summer and winter seasons, and the weather and irradiance data are obtained from Solcast API. In order to find out the effectiveness of different solar proxy settings, we test out 4 different settings based on our method. As we discussed before, a large number of real proxies may not always be available in practice. So we test out the proxy setting with the combination of synthetic solar proxies. The solar output of these synthetic proxies is calculated by the physical PV model and the citywide weather data. Here we have 3 proxy settings which directly use 3 real solar proxy, and we also have 1P plus 1 SP, 1P plus 3 SP, and 3 SP. The SP means the synthetic proxy. Table 1 shows the parameter we set for those synthetic proxies. Since tilt and DC rating only scale the solar generation up and down, only the orientation will shift the solar generation peak time. So we can set up same tilt and DC rating value because our method can help us adjust weight vector in solar mixture model. From table 1, if combining with only one synthetic proxy, we set the orientation of this proxy to face north, which is the best choice for PV system located on south hemisphere. 3 synthetic proxies have 2 additional proxies facing east and west respectively. 2 state-of-the-art baseline methods are also implemented. Baseline 1 directly uses the physical PV model to estimate the solar generation. Similar to ours, baseline 2 uses the real solar proxy to estimate the solar generation. So to be fair, in our experiments, we use the same real solar proxy for our method and baseline 2. We use root mean square error and normalized root mean square error matrix to evaluate the disaggregation performance. Here, NRMSE is the RMSE normalized by the mean value of the real generation. Table 1 here shows the performance comparison of disaggregation method. As we can see, 3 proxies yield the lowest error among all the methods. And when we compare 1P plus 3 SP with 2 baselines, we can see that using only 1 real proxy, our method still can beat 2 baselines, even though baseline 2 also use the same real proxy. And if we compare 1P plus 3 SP with our 3 SP, we can see that without the measurement from real proxy, the performance will decrease, since real proxy can capture the abrupt changes in solar generation, which cannot be captured by synthetic proxy. In the comparison between 1P plus 3 SP and 1P plus 1 SP, 3 SP here has 2 additional synthetic proxy with different orientations, can help shift estimated peak generation time closer to real solar NILM. Except evaluating solar disaggregation performance, we also want to study the effect of behind-the-meter solar generation on the performance of NILM techniques. In other words, we want to see if it is necessary to disaggregate solar power from net load before trying to separate the household demand into the appliance consumption. Since normally the NILM techniques are tested under the condition there is no solar system installed, which means that the collected net load data will directly be the aggregated appliance consumption. In this experiment, we use 1-minute resolution data from Pecan Street. The NILM performance is evaluated by applying 2 popular techniques. The first, the performance is evaluated on the real home load, net load, and estimated home load using different solar disaggregation methods. This plot shows the NILM disaggregation performance. As we can see, the performance is roughly the same for most appliances except for AC. If you look at the last group, the overall group, we can see from the results of our method and net load that solar disaggregation does improve the overall NILM accuracy. Since the dataset is from summertime, the most significant appliance consumption will be AC demand. As we can see, if we directly apply the NILM on net load data, the performance significantly decreases in air conditioner disaggregation. Here list 2 takeaways we find important from our work. First, real proxy measurements can be replaced with synthetic ones to achieve comparable performance in the solar disaggregation task, as long as there is one real proxy. Second, running solar disaggregation first can improve the accuracy of NILM methods for the customer with rooftop PV systems. Thank you.
Again, a very interesting field of application. Thanks for the video. Now my question, is one of the authors present? No, that doesn't seem to be the case. So let me ask you again to add any questions to our Slack channel, and the authors will then answer these questions on the Slack channel. With that, I would like to thank all of the speakers again, and also all of you joining this session. I thought it was very interesting. And with that, I can conclude the session. And also many thanks to Zoom masters, Faisal and Ram. Thanks for making this so smooth. And I hand back to you. I think we now have a 35-minute break, right?
Yes,
that's right.
Break. Yeah.
Yeah. And if I got this correctly before, we are not going to do breakout sessions in this